Hello everyone. My presentation is on the new contextual Martian-Bandit algorithm for a semi-parametric reward model. And this is a joint work with my advisor, Professor Gi-Soo Kim. The goal of mobile health is to encourage the user's healthy behavior, namely reward, through sequential interventions such as pushing particular messages. But at the beginning, it is unknown which interventions yield maximum reward. Therefore, the mobile health system has to adapt its action choices or policy in the course of delivering the interventions and receiving the rewards. So this process calls for reinforcement learning methods. Besides mobile health, there is a wide variety of applications, including news article recommendation algorithms, web page ad placement algorithms, revenue management, marketing, and recommendation systems. Actually, in this study, we did not have data from mobile health yet. So instead, we used a news article recommendation log data that is provided by Yahoo and that is publicly available. And we applied the proposed method on this data. So we'll take a close look at the settings. Every time a user logs in the Yahoo web page, the Yahoo system selects one article among a large pool of many articles, and the system displays the selected article on the main position, which is called the feature tab. Then the visiting user clicks the article only if he or she is interested in the contents. And based on whether a user has clicked or not the article, the system updates its article selection strategy. And the system repeats this whole process over time. And one thing that should be noted is that in this setting and also in many other reinforcement learning settings, whether a user would have clicked or not the article, which is the reward, is only observed for the selected articles. And for unselected articles, the reward remains missing. So such kind of problem can be framed as a Martian-Bandit problem. And recently, researchers at Yahoo proposed a contextual bandit algorithm which uses site information of the user and articles. And they increased the total number of clicks by 12.5% compared to a context-free bandit algorithm. And then the paper of Abbasi, Yakori et al. Demonstrated a tight, high probability upper bound for the regret, a performance measure of the Yahoo team's algorithm. But still, the Yahoo team's method relies on restrictive assumptions on the distribution of rewards. So the goal of this work was to propose a novel contextual bandit algorithm that performs well under a relaxed assumptions. You must be very familiar with this figure and the settings, so I will very briefly introduce. The octopus describes the learner, and at each time, the learner is given a total of n options of actions. And the actions are described as the arms of the bandit machines, and pulling each arm returns a specific reward. So we let the RIT be the reward given by the iced action at time t. And the classic bandit problem assumes that the expectation of the reward is fixed as theta I. Then at time t, the learner chooses one action, denoted by AT, and observes the reward RATT. And under this setting, the goal of the learner is to maximize the average of observed rewards among a total of t steps. We let theta star be the largest value of theta, then the performance measure, regret at time t, can be defined as the difference between this maximum theta and the theta of the chosen action. And under that, the goal of maximizing the average of observed rewards is in fact equivalent to minimizing the average regret, RT. But since the values of zetas are unknown, the learner's job is to learn these values by pulling arms and receiving rewards. But as we have seen in the news article example, only one reward, RATT, is observed among the whole reward vector. And therefore, the Bandit problem is basically a problem of how to balance well between exploitation and exploration. But in the classic Bandit problem that we had viewed, each arm I has a fixed reward distribution that does not change over time, and this can be a little restrictive in applications like mobile health. The contextual Bandit problem extends to more realistic settings where there is a site information, context vector, BIT of dimension d that is associated with each arm I at time t. And we assume that the expectation of reward depends on the site information. And from now on, there isn't any best arm anymore because the arm that gives maximum reward will change over time. So now the goal is not finding the best arm, but finding a good policy that maps context to actions. Specifically, linear Bandit algorithm assume that this expectation of the reward is linear in the context vector, where mu is an unknown regression coefficient. And we additionally assume that the errors, eta it, are R sub Gaussian. This R sub Gaussian assumption includes not only the Gaussian assumption, but also any kind of bounded distribution. Therefore, this R sub Gaussian assumption is, I think it is a weak assumption. And finally, we assume that the norms of the context and mu are bounded. So in linear bandits, the optimal arm A star T changes over time. This is the one that maximizes the B transpose mu. And the regret at time T is expressed as follows. And for the linear bandit problem, lower bounds have been proven for the average regret. First, when the number of actions n is infinite, Danny et al. Proved that no algorithm can achieve lower bound than of order d over root t. And when the number of actions is finite, Chu et al. Proved a lower bound of root d over root t. So we can see that the lower bounds depend on the dimension of mu. So I will briefly review the existing linear algorithm because for comparison purpose with our proposed method. So the first one is the well-known upper confidence bound algorithm, also called the UCB algorithm. This algorithm computes at each time the upper confidence bound of the reward of each arm, and then it selects the arm which has the highest UCB. Since the UCB reflects the current estimate of the reward, and plus its uncertainty, it is known to naturally trade off between exploitation and exploration. Specifically, at each time, the algorithm updates the estimate of mu, and based on that, computes the upper confidence bounds of each arm like this, where here, this is the current estimate of the reward plus an uncertainty part. And alpha is a positive constant that controls the degree of exploration. Then the algorithm pulls the arm that maximizes the UCB. As for the estimator mu hat, a simple linear regression estimate is used, which is computed using the pair of observed context and observed rewards. But at the beginning, since there are 0 observations, the denominator BT is set as the identity matrix. And we know that this is like doing L2 regularization. And one thing that I want to point out is that in practice, this value alpha, the best method to set the value of alpha is by setting it as a tuning parameter. So in my case, I use a validation data to decide which value to use for alpha. But in a theoretical part, in a theoretical aspect, Abbasi, Yakori et al. Showed that if we set the value of alpha like this, then the sum of the regret, which is t times the average regret, can be bounded by the right-hand side with high probability. And dividing both sides by large t, we can see that the right-hand side is approximately d over root t times some small terms. Therefore, this bound is very close to the lower bounds. So I will see very briefly the proof. In fact, the key of the proof is proving inequality 1. And this inequality bounds with high probability this term when alpha is set like this. And this is equivalent to saying that the upper confidence bounds are indeed 1 minus delta probability upper confidence bound for the expected rewards. So the core of the proof, in fact, is proving 1. And once this is established, then the rest of the proof is very simple, and I will just skip the details. So proving 1 was the key in the UCB algorithm. And proving 1 is about bounding this term with high probability. And using very simple techniques, we can bound this term by the STI times some blue term plus 1. So if we bound this blue term plus 1 by alpha, then the proof is completed. This blue term involves the observed context b tau and the errors of the observed rewards eta tau. So therefore, it seems to be simple to bound this blue term using the R sub Gaussian assumptions. But however, bounding the blue term was not trivial because the errors of the observed rewards are not independent Gaussian given the observed context. Sorry if you are very familiar with this. But Abashi, Yakori et al. Derived the bound of this blue term by using that although the etas are not independent, the observed eta given the history is the union of the past actions, past rewards, and past context. Then given the history and the current context, then eta taus are R sub Gaussian. So they use this fact, and therefore the etas are, although they are not independent, they are martingale difference sequences. And using that fact, they use the corollary of the Lapeignac and easily derive the bound of the blue term. The next algorithm is the Thompson sampling algorithm. Simply put, this algorithm is a randomized version of the UCB algorithm. So the heuristic is to pull the arm according to the posterior probability that it is the optimal arm. So the algorithm is very similar to the UCB algorithm, except that instead of computing the upper confidence bounds, the algorithm samples a random utilde from the posterior distribution, which has mean mu hat and variance v square b inverse. Then the algorithm pulls the arm AT that maximizes the B transpose mu tilde. Otherwise, the estimator for mu is the same as the previous UCB algorithm. And here we can see that the distribution of B transpose mu tilde is like this, where the mean is the current estimate and the variance is V square STI square. And here the standard deviation, V STI, is actually the same as alpha STI of the UCB algorithm if we set V to be like this. So UCB and Thompson sampling algorithm are very closely related. The main difference is just that the UCB is deterministic, while the Thompson sampling algorithm is randomized. And to derive this posterior distribution, we just put a Gaussian prior on mu, and also we assume that the reward given mu is Gaussian as well. But however, Agrol and Goyle show that these Gaussian assumptions are not necessary to proving this regret bound. And this regret bound is close to the bound of UCB algorithm, but it's slightly worse because it depends on D to D3 over 2 instead of just D. And this is interpreted as a price for randomness. So far, we have reviewed two linear bandit algorithms, and these linear algorithms rely on restrictive linear assumptions, because the restrictive part is that the relationship, which is expressed by the coefficient mu, is time invariant. So this is like a weak part. In contrast, adversarial bandit algorithm constitute another big branch. These algorithms do not impose any assumption on the reward, except that the reward is bounded. Therefore, the distribution of the reward is allowed to change over time, and it can also change according to the past, adaptively. In the extreme, it is assumed to be controlled by an adversary. But however, instead of greatly mitigating the assumption, it is very hard to achieve a low regret with respect to the best choice, S star T. So in this area, instead of minimizing this regret, we predefine some finite number of policies, and we target to minimize the regret with respect to the best policy among the finite ones. So Beiger, Zeimer et al. Proposed the EXP4P algorithm, and I will skip the details, but I just note that they use a weaker notion of regret, which is with this term is the maximum total reward among the finite K policies. And in conclusion, their algorithm achieved the following regret bound for the weaker notion of regret. And we can see that this is also sublinear in T, but however, this bound depends on the number of actions and also on the number of policies, K. And for this weak regret to be close to the more conservative regret, then K should be as large as possible to contain the real optimal policy. Therefore, this is actually very large in practice, and this can be ineffective. So in our work, we considered a compromise between simple but weak linear bandit algorithm and complex adversarial algorithm, which is a semi-parametric bandit problem. Actually, for those who are here yesterday, this is actually the same reward model, non-stationary reward model that was addressed by the work of Professor Murphy. So this is identical. In fact, this is identical, but I would like to point out that in our work, we consider a little bit different setting, and this setting requires for a new algorithm. And I will elaborate on that later. So the semi-parametric model assumes that we define the history until time minus 1 as before as ht minus 1, and we define the filtration as the union of the history and the current context. Then the semi-parametric reward model assumes that given this filtration, the expectation of reward is consisted of two components, where the first component is the linear part, which has a time invariant linear relationship with the context, and the other term is a non-parametric term that depends on the time and possibly on the past, but does not depend on the action. Our remark is that if we set this nu t to be 0, then the problem is just a linear bandit problem. But if we set nu t to depend on the action as well, then this problem can only be addressed by adversarial bandit algorithms. We make the usual additional assumptions that given filtration, the errors are sub-Gaussian, and also the norms of the context and mu and nu are bounded. There can be several interpretations of this nu t. In mobile health, nu t can represent the amount of healthy behavior when no intervention is delivered. So this baseline behavior can change with time depending on the abrupt mood of the user or depending on the intervention delivered in the past and the user's past responses. So whether there was too much interventions or too less interventions. And in the news article example, this nu t can represent the baseline tendency of the user visiting a time t to click any article, regardless of the contents of the article. And this can change with time because different users visit at each time. So their tendency will be different. And even for the same user, the clicking tendency can change according to the user's mood or schedule. So, and this important fact is that such kind of user's mood or schedule cannot be captured as the site information. Therefore, this cannot be kept here. So they should be dealt with here. There's some remarks regarding the semi-parametric model. First of all, we don't impose any assumption on the complexity of nu t, so nu t can change, is allowed to change abruptly. And the optimal action A star t does not depend on nu t because nu t does not depend on actions. Therefore, we are not required to estimate this intercept nu t for maximizing in the purpose of maximizing a reward. Also, the regret at time t does not involve nu t as well because they are canceled out. But still, we need to take care well of this nu t because it confounds the estimation of the regression coefficient. And given that only one observation is allowed at each time, it is difficult to distinguish between the nu t and the linear part. So there are two existing methods that consider the same reward model. The first one is the one that was presented yesterday by Professor Murphy. And it is the action-centered Thompson sampling algorithm. I will call it ACTS. ACTS assumes that the first action is a kind of base action where the context is 0. And then ACTS uses the frame of the Thompson sampling algorithm, but in two stages. In the first stage, it chooses a non-base action A bar T from action 2 to action N. And in the second stage, the algorithm pulls the arm A bar T with probability PT and the first arm with probability 1 minus PT. And in the second stage, we can actually compute this probability using the Gaussian assumption of mu tilde because we are using the Thompson sampling framework. But so this is computed like this. But however, Professor Murphy emphasized yesterday that we should constrain this probability to lie between predefined values Pmin and Pmax. And the reason to put this constraint was to prevent the algorithm to converge to deterministic algorithm. Because in mobile health, deterministic algorithm correspond to either not sending any message at all or sending the same message every time. Therefore, this deterministic algorithm can be ineffective in the mobile health setting. Therefore, we should constrain the action choice probability. And to cancel out the problematic Nutti term, SCTS used the pseudo reward, which is the actual reward multiplied by this term, which is the indicator that the non-base action was pulled minus its probability. And yesterday, Professor Murphy referred it as the contrast coding, if you remember. And the important fact of the pseudo reward is that its expectation does not depend on the Nutti anymore. So this is the algorithm, and this algorithm performs very well. Because the regret bound, the bound of the sum of regret is bounded by a term that is comparative to the original Thompson sampling algorithm for linear models. But however, in fact, in this bound, a constant m is multiplied here, which is 1 over p min times 1 minus p max. And in the setting of SCTS, since we constrain the probabilities, this constant is not a problem. But in our work, we wanted to consider the case where we allow the policy to converge to deterministic policies. So in that case, we should set p min 0 and p max to 1. Therefore, m can be very large, can explode, and in our case, m is problematic. So, to overcome this problem, Krishnamurthy et al. Proposed a different algorithm, which is called the Bose algorithm. This algorithm takes a different approach from previous method. It takes an action elimination method, where at each time t, the ith action is eliminated if there exists another action j, such as the following inequality holds. And this means that the ith action is suboptimal at that time. And here the constant omega controls the degree of elimination. So here omega is set as a tuning parameter. And then among the survived actions, the real action is chosen randomly according to a specific distribution pi, where pi it is the probability of pulling the ith arm at time t. And finally, for estimating mu, the authors proposed to use a centering trick on the context vectors. And they centered the observed context by subtracting its conditional expectation b bar tau, which is defined like this. And denoting this center vector as x tau, they propose this estimator, which looks similar to the original linear estimator, except that the b taus are replaced with x tau. And there is a constant here, positive constant gamma. The Bose algorithm, a great advantage of the Bose algorithm is that it achieves a very tight bound, because it depends on d instead of d to d3 over 2. It is a great advantage, but however, there are some problems of this algorithm. First of all, the action elimination step requires to compare every pair of the actions, every possible pair of the actions, so it requires ON square computation. And the distribution pi should satisfy a specific condition to guarantee the above regret bound. But however, the authors only show that there exists such pi, but they did not solve the solution for that condition when the number of action is greater than 2. And a third problem is that this regret bound is only valid when the gamma, which was here, is bigger than this value. And this value can be very, very high, because for example, in the news article example, if we take delta to be 0.1, then gamma is over 2,400. And in practice, gamma can be set as a tuning parameter. Then if we set it as a tuning parameter, the algorithm requires 2 sets of tuning parameters, which can delay the computation. So now comes the proposed method. We propose to use the Thompson sampling framework, but we propose to use a new century trick on the context that doesn't require any tuning parameter gamma. The reason that we use the Thompson sampling framework is because the pi it, the probability of pulling the ith arm at time t, is determined by the distribution of mu tilde. So it can be easily derived and doesn't need to be solved from a specific condition. And second, we propose the following estimator for mu, where it is similar to the estimator of Krishnamurthy, but in the denominator there is a new term, the expectation of x tau and tau transpose. And instead of introducing this new term, we don't require any big constant gamma on the regularization. I just wanted to show that the B bar tau used in centering and the new term x tau, the expectation of x tau transpose can be easily computed using the probabilities pi. And using that, the proposed algorithm is as follows. And it is identical to the Thompson sampling algorithm, except that there is a step for computing the action choice probabilities explicitly, and the estimator for mu is different. And the main contribution of our work is a new theorem for bounding this term by the right-hand side. And when nu t was 0 in linear bandits, then linear bandits, when nu t was 0, we had a similar bound for a similar term, and we can see that the two bounds are comparable. I think it is too technical, so I will just quickly show you some new aspects in the proof. First, using similar techniques as in the linear case, we could bound this term by STI times 4 terms, where the 4 terms are represented here. And here you can see the first term involves the errors. So the first term is actually a similar term that arises in the proof for linear bandits as well. And the fourth term is a very small term. So the problems are the two blue terms that arise because of the semi-parametric assumption, and also because of the use of a new denominator. Here, d tau is defined as x tau transpose minus its expectation. But remember that for bounding the first term, we had used that the errors are martingale difference sequences. And so we had bounded using the corollary of the Lapénia, the first bound easily. And the new problem is to bound the second term. But however, in the second term, these terms are not R sub Gaussian anymore, so we cannot use the same technique. But however, the x tau here are vector valued martingale difference sequences. So using a slightly different lemma, we could obtain a similar inequality required to derive the bound. And this is where this is the reason why we needed a new term in the denominator. And we bounded the third term using a similar technique with some additional work. And so in conclusion, we could bound all the 4 terms and complete the proof. Sorry for being too technical. And in conclusion, we proved that the proposed algorithm achieves a tight regret bound for the sum of regret, where this bound is the same as the original Thompson sampling algorithm, and this bound does not involve any big constant like m. So this bound holds even when we don't restrict the action choice probabilities. This is the summary of what I wanted to say, so you just need to remember this table, I think. So this table summarizes the properties of the three semi-parametric bandit algorithms. The first one is ACTS by the work of Professor Murphy. The second is Bose algorithm of Krishnamurti. And the third is the proposed Thompson sampling algorithm. And I would like to emphasize that our algorithm does not restrict policies from converging to deterministic policies. And the derivation of the action selection distribution is straightforward from mu tilde. Also, the number of computations per time is moderate and only requires one tuning parameter. And the regret bound does not involve a big constant like m. Yes.
For the ACT,
yes.
How reliant is their proof of the regret bound on that? Because I thought that restriction was like mostly a practical kind of consideration where you don't want to just skip one message, but is the proof pretty? How is the proof reliant on that?
Okay. In fact, I think the one reason is, as you said, a practical reason to prevent from converging to deterministic policies. But the second reason is that without this, the regret bound can explode because in the ACTS algorithm, the ACTS algorithm, we use the pseudo reward for estimating the regression coefficient mu. And here, since the expectation of pseudo reward looks like this, then we should include in the denominator this factor. And this results in this goes to in the regret bound, this results in a factor like this. So it is bounded by the constant m. And so we conducted simulations to compare the three semi-parametric algorithm and also the original Thompson sampling algorithm. We set the number of arms to be either 2 or 6, where when the number of arms is 6, then the Bose algorithm cannot be implemented. And we set the dimension of the context x10 and assumed a semi-parametric reward. The left plot is the median of the cumulative regret over 30 simulations, and the right figure is the medians and also the 25 and 75 percentiles of each algorithm. So they are expressed in dashed lines. And when nu t is 0, when the reward is linear, then the original algorithm performs the best. And the three other algorithms are slower, but they are comparative. In the second case, I set the nu t to be like this. It can be a little strange. It was just for simulation. And in that case, the original algorithm performs the worst, and the three others are comparative. In the third case, I set nu t to be increasing with time. And in that case, also, the original algorithm performs the worst. When n is 6, there were some differences between the ACTS algorithm and the proposed algorithm, probably because of the big constant m. And when nut is 0, the original is the best. But when nut varies with time, then the proposed is the best. And SCTS somehow performs the worst. And when nut is increasing, then in that case as well, the proposed one performs the best. This is the final section of my presentation. I applied the proposed method and also the existing method to the Yahoo data, which is the data of user clicks for the news articles displayed in the feature tab of the Yahoo front page. And this is the same data that Professor Ri-Sung used for application. So a brief explanation. The data is log data from May 1st to May 10th of 2009, and it is corresponded to 45 million user visits. And at every visit, one article was chosen uniformly at random from a total of 20 articles and was displayed in the feature tab. So you can see that this data was generated using a uniform random policy instead of any online learning policy. And the reward is whether a user clicked the article. And for each article, there was a context vector of dimension 35. And since the logging policy is different from the policy that we want to evaluate, we use the off-policy evaluation method of Lee et al. And this is the same method used by Professor Ri-Sung. So the method is very simple. Given the whole stream of events from the original data, we just pick up the events that matches the choices of the target policies. Then we can construct an unbiased reward estimate of the target policy. And using that, we report the mean first quartile and third quartile of the user click numbers achieved by 3 algorithms over 10 runs. And you can see that compare the uniform policy, the Thompson sampling algorithm performs much better. And compared to that, the proposed TS algorithm increased the number of user clicks by over 4.4%. So in conclusion, we wanted to propose a new contextual MAB algorithm for non-stationary semi-parametric real model. And the proposed method, we would like to say the proposed method is less restrictive, easier to implement, and faster than the 2 alternative algorithms. And the proposed method achieves a regret bound very tight. And we are currently extending this method to nonlinear case. And this is in progress. Thank you very much for listening. I didn't told you. I said since I think I didn't give restrictions. So here in the ACTA's algorithm, ACTA's algorithm, we need to constrain between Pmin and Pmax, but I set the Pmin 0 and Pmax 1. But in fact, the results are similar when I put like Pmin 0.1 and Pmax 0.9. The results were similar. So I don't know exactly why, but this didn't change the result much. In that case, but because of the regret bound, I think it will not. But in some cases, in simulation, there are some cases that the PT that is before constraining, the computed PT is 0.3, like we don't need to constrain that probability because it is already inside the constraint. So there are some cases like that, and in those cases, I think it will converge. But in the cases, but if the computed probability here, if the computed probability here is 0, then and we don't give any constraint, then I don't think it will converge.